class. In this lesson, we will be discussing about probability. In the last lesson, we discussed about the introduction to statistics, and probability is a very important aspect of statistics. So if you are yet to watch the previous lesson, kindly go and visit it for you to have a better understanding about what we'll be doing in the subsequent lesson. If you are new to my channel, don't forget to use the subscribe button, like, comment, and share the videos to those that will find it helpful. So without further ado, let's move into this lesson. So in this lesson, we'll be discussing about probability. So when we hear about probability might not be a new word to some of us, and it might be new to some. So what I want you to understand about probability is that when we're talking about probability basically deals with events. When we're talking about probability, then an event must be happening. So the likelihood of the occurrence of an event is definitely what we mean by probability. So, for example, if I say the likelihood of rain falling today is 0, what I'm saying in a sense is that the probability of rain falling today is 0. That is, there is no possibility of rain falling. But if I say the likelihood of rain falling today is 1, what I'm saying is that rain will certainly fall today. So from that information, you should know from this point that probability will only range from what? From 0 to 1. You can never have your probability as minus. You can never have it as -1 or -2 and so on. You can never have it greater than 1. You can never have a probability as 2 and the likes. So when you are doing any analysis on probability and you start having those odd numbers, all in the sense that is numbers that are not within 0 to 1. I'm not saying odd number and even number. No, that's not what I'm saying in this essence, in this context. So have that in mind. Probability will range from what? From 0 to 1. From 0 to 1. So in probability, what we need to understand, as we discussed in the first lesson, that is the gross statistics. There's some terminologies as well that we should take note in probability. Terminologies including terminologies like trials, terminologies like sample space, terminologies like events. So what we need to understand by event is basically subset of sample space. So when we're talking about trial is basically repeated operation. That is operation in which we keep on repeating. That's trial. So we're talking about experiment. So that is experiment is also more of trials. That is the operation being carried out. But trials is now telling us that we're repeating it, to get more accurate data. So we also have outcome. So outcome is basically the result of the experiment. So outcome, and we also have a term known as the random experiment. So what do you mean by random experiment? That is, the random experiment is the one in which we cannot predict. That is, we cannot predict the result beforehand. We cannot predict the result. We cannot predict the outcome of that experiment. So that's when it is the random experiment. So what about sample space? Sample space is basically the set of all possible outcomes of any random experiment. So that's the reason why we have to generate a sample space for dice. So what are you doing in that situation? You are basically putting all the possible outcomes in that sample space. Same thing applies to a coin. When you throw a coin, head, tail, and the likes, when you're generating a sample space, that is all possible outcomes in that experiment is basically your sample space. So please kindly take note of those things. Probability can only, please take note, it can only range from what? From 0 So that's I tell us that 0, 0 is less than or equals to probability less than or equals to what? Or equals to 1. That is what is trying to tell you that probability can be equals to 0 or greater than what? Than 0. If 0 is less than probability, definitely probability is greater than 0. So I'm also telling you that probability can be equals to 1 or less than 1. So probability can never move out from this range. Please kindly take note of that. So and also take note, when probability is 0, it means the event can never happen. And when probability is 1, it means that the event will certainly happen. The event will certainly happen. So this tries to tell us that probability is a non-negative, can never be negative. Is a what? Is a non-negative real number. It is a non-negative, it is non-negative, and it's also what? It's also real. That is, it can never be imaginary. So when you are dealing with probability, you can never be having the complex form. You can never be having IG and the likes. Do you understand? So it is always a real number having the real part on it. It can never have the imaginary part. Please take note of that. It's a non-negative real number. It's a non-negative real number. Please take note of that. Like this, you need to take note in probability. And also probability of sample space. Please take note of that. Because we'll be needing these things as we move on. Probability of sample space. Probability of the sample space. Probability of the sample space, which is P of S, is always equals to 1. Probability of sample space is always what? Is always equals to 1. Why is it equals to 1? Because the entire sample space, probability is basically the element in mosaic divided by the total number of elements. But when you're talking about probability, the sample space contains all the elements divided by all the elements. That makes it always 1. You understand the idea? So that's another point you should note about probability. So and also take note that the probability of an empty set is also 0. Probability of an empty set. Probability of an empty set is 0. Fine. What does it represent? It represents an empty set. That is a null set. So probability is 0. So can you take note of those things in probability? So let's discuss about some rules in probability. Some rules in probability. Some rules in probability. So what are the rules? Rules. We're talking about rules. We're talking about theorem as well. So let's say we have theorem 1. Theorem 1. What does theorem 1 says? So theorem 1 says if A and A prime are complementary events, that is A is the complement of A prime and A prime is the complement of A. So are what? Are complementary. Event. If they are complementary events in a sample space, in a sample space, in a tells us that the probability of A complement is equals to 1 minus probability of A. Please, kindly take note of this. Kindly take note of this theorem, because this theorem will be very important for you when you get to complex calculation. So you don't have to be stressing your brain. So once you just remember the theorem, then you'll be able to apply it. So the first theorem is that if A and A complement are complementary events in a sample space, that is, for this theorem to be true, A and A complement must be in the same sample space. And it says if A is a complement, so complement in mathematics, for let's say for those of us who have done sets before, when talking about complement, we're basically talking about opposite. Let's put it that way. Or not even opposite. Let's say that is elements that are not in. Let's put it that way. Elements that are not in. So let's say A comprises of 1 to 5. A comprises of 1 to 5. And it is in a sample space. But in that sample space, you also have elements like 10, let's say 6 to 10. So that tells you that elements that are not in A are what? Are A complement. Elements that are not in A are A complement. So definitely from 6 to 10, they are what? They are A complement. So that's what this aspect is trying to explain to you. So we also have another theorem, which is theorem 2. We'll be needing all these theorems, so that's the reason I'm taking my time to explain. So theorem 2. What theorem 2 says? Let me try to prove this. Let me try to prove this theorem now, because some of us might be needing the proving and may be asked in some exam cases. So you want to prove this, we said A and A complement are elements in what? In a sample space. Are elements in a sample space. It tells you that, and I told us that A complements are elements that are not A, but they are both in what? They are both in the sample space. That tells you that the total of A and A complements make up the sample space. So automatically, so let's prove it. So the proof, I'm about to need the proof of theorem 1. So it tells you that A union A complement should give you what? Should give you the sample space. Should give you what? The sample space. What does union mean? Union means everything together. Everything together. While intersection means the common between them. The common between them. So A intersection A complement is basically 0. Because when you have A and you have A complement, you cannot have some element that will common to both A and A complement, since A complement is basically things that are not in A. So you cannot, you understand. So for A union A complement will definitely be the whole, the whole sample space. So since A union A complement is equal to the whole sample space, and as I told you, A intersection A complement is basically an empty set. That is, you cannot have something that is common to both of them. So what do we represent empty set as? We represent empty set as what? As 5. We represent empty set as what? As 5. So and that's how it tells you. And if you're using or rewriting them, you can say N. You can say A union A complement. Just introducing it. That is, we are more concerned of the number in that set rather than the element in the set. So A, that is A union A complement, since A union A complement is equal to S. So number of A union A complement will be equal to number of S. Will be equal to number of S. Kindly take note of that. Will be equal to number of S. So now we're talking about probability. Probability. I have explained to us earlier that probability is basically the number of a particular element in concern divided by the number of the entire sample space. Divided by the number of the entire sample space. So in this situation, if you have the number of A union A complement over the number of sample space, you know, A union A complement, what does it give us? It gives us the number of sample space. So that definitely tells you that this is what the number of sample space divided by the number of sample space. And this cancels this, definitely gives you 1. Definitely gives you what? Definitely gives you 1. So that's automatically tells you that the probability of A union A complement is equal to what? Is equal to 1. Is equal to 1. Because what we try to do here is to find the probability of A union A complement. And which is what? The number of A union A complement divided by what? The number of sample space. I already explained it before I did the calculation. So that's another step in proving that this theory is what? Is correct. But we know from our set, and that should be our distributive law. So we have A union A complement, which is given as probability of A plus probability of A complement minus probability of A intersection A complement. It's a rule. This is a rule which you need to know. Please know this rule. Know this rule offhand. Know this rule offhand. When you are arguing, this is for 2 elements. We also have one for 3. That is A union A, or let's say A union B union C. You can also rewrite it out like in this form. So please take note of this. You must know it offhand. So for you to be able to to proceed in aspects like this. So and we already know that A intersection A complement is empty set from here. A intersection A complement is empty set. Automatically, I already know that the probability of empty set is what? Is 0. Probability of empty set is what? Is 0. So since probability of A intersection A complement is equal to probability of what? Of empty set, which is equal to what? Equal to 0. Very easy. So automatically, the probability of A union A complement is definitely the probability of A plus probability of A complement. Because this is 0 already, minus 0, you don't need to stress yourself about that. You don't need to write anything. You don't need to write anything. So we already know that probability of A union A complement from here is 1, because A union A complement is what? Is your sample space. Is your entire sample space, and probability of sample space is what? Probability of sample space is 1. We already said it from here. So automatically 1 equals to what? Probability of A plus probability of A complement. So you can now prove this. So automatically probability of A complement will be equal to what? 1 minus probability of A, and vice versa. Also probability of A will be equal to what? Will be equal to 1 minus probability of A complement, which is proved. Which is proved. Let's move to the second theorem of probability. theorem says? What does the second theorem says? The second theorem says the probability of an empty set is 0, in which you have been using. We have even applied it before. Yes, the probability of empty sets is 0. So that's the next theorem for what? For any sample space. For any sample space. So it is just more of a reminder. It is a reminder to make sure it's at the back of the mind. So to prove this, since the sample space your S union empty set, you have a sample space together with empty set, so you are still left with your sample space. You are still left with your sample space, you are still left with S. So that tells you that the probability of S union empty set should give me the probability of what? Of S. Should give me the probability of S. So we can write this. We can say the probability of S union 5. So if you want to write that in this form, so you can say this is definitely equals to the probability of S plus the probability of 5 minus the probability of S intersection 5 that is probability of sample space intersection empty set. Probability of sample space intersection empty set. So and what would that give us? We already said this is equal to S. This is equal to sample space. So we can definitely equate this. We can say probability of sample space is still equals to this. So the probability of sample space intersection empty set is definitely 0. It's definitely 0 because it is not. You can't have something that is common between a sample space and empty set. So it is 0. So definitely you have probability of sample space equals to probability of sample space plus probability of what? Of empty set. So we can now say probability of empty set is equal to probability of S minus probability of S, which is definitely 0. So that tells you that the probability of empty set is equal to 0. So that's the whole proof. That's theorem 2. So let's move to theorem 3. Mind you, an examiner can ask you to prove all theorem in an exam. So please make sure you have everything at the back of your mind. So theorem 3. Theorem 3 says 0 less than or equals to the probability of A less than or equals to 1 for any event. That is, and these things are things we've explained even before we started all this theorem. We've explained all this. That is, we said probability can only range from what? From 0 to 1. So we cannot have probability of minus 0. We cannot have probability of I said minus 0. We cannot have probability of minus 1. We cannot have minus 2. You cannot have probability greater than 1. You cannot have probability like 2, 3, and the likes. That can never be possible. So for the proof of this, what we really need to know about is that using the fact that an empty set file is contained in an event A, and event A is also contained in a sample space, which is definitely true. An empty set is a subset of every single set. That is, if you are asked to list out a subset for a particular set, you must include an empty set. Empty set is a member of all sets. So let's say an empty set is contained in A, and A is contained in a sample space S. E is contained in a sample space S. Definitely, the probability of phi is less than or equals to the probability of A less than or equals to the probability of S less than or equals to the probability of S, which is very true because this is a member of A and A is a member of this subset. So definitely the probability of phi will be less than or equals to the probability of A, and probability of A will be less than or equals to the probability of S. But remember, the probability of phi is equals to what? Is equals to 0. And probability of X is equals to what? Is equals to 1. So that tells you that 0 is less than or equals to 1 and less than or equals to what? Or equals to less than or equals to less than or equals to probability of A and less than or equals to probability of A and less than or equals to 1, which I have included. So that's another theorem. So let's move to the next theorem, which is theorem 4. So what is theorem 4 says? Theorem 4 says if A and B are any two events in a sample space S, if A and B are any two events in a sample space S, if A and B are any two events in a sample space S, then the probability of A union B, the probability of A union B is given as the probability of A plus probability of B minus probability of A intersection B. And mind you, we have been using this rule even before we stated the theory or theorem. So we have been using this rule. So we are going to prove the reason why this is true. And we begin that with the concept of set. I believe you all remember the concept of set, that is particularly Venn diagram. So let's say we have a Venn diagram. Let's say we have a Venn diagram here. So Venn diagram of, we're having two events. So the Venn diagram will be having two circles. So one for event A and the other for event B. And this is the intersection of the two events. Right? And the entire sample space, everything, both A and B, both A and B, A complement and likes, everything represents the sample space. Right? And we also have the universal. The O that contains the O set. So here we have small a, let's call this B, small b, or let's call this B, let's call this C. So what does this small a mean? It means A alone, that is it's only A, that is we don't want the one that we share with B. So this small a means A only. This C means that capital B only. While this small b means what? Their intersection. So the probability of A union B, A union B, A union B is everything in A and B. Everything in A and B is your A union B, which is basically your A plus B plus C. That's A union B. So that tells us that this is what probability of small a plus probability of small b plus probability of small c plus probability of small c. Probability of small a, probability of small b plus probability of small c. And what is our probability of small a? That is A only. What does A only mean? That is, you only want A, you don't want B. You only want A. So what that trying to tell us is trying to tell us that A only similarly interprets as what? As A small a capital A union capital A intersection B complement. Small a interpret as capital A intersection B complement. Capital A intersection B complement. B complement in the sense that everything that is not B, everything that is not B, and everything that is not B include what? Include everything here. So this small b already belongs to B. Everything that is not capital B will definitely be A. And it will also include everything outside here as well. That's the reason why we are introducing intersection, that is A and the common between everything in A and everything that also belongs to B, which will only be everything in A only. In A only. And that will definitely be the probability of A intersection B complement. Intersection B complement. So what will be for small b? Small b is definitely the intersection between A and B. So that was probability of A intersection B. Probability of A intersection B. Then the same thing applies to C. The same thing that applies to A applies to C. So if you need B only is your small c. B only is your small c, which is definitely the probability of A complement plus B. So it's more of saying, plus intersection. It's more of saying probability of B intersection A complement. But you know, it will make more sense to bring A before B. So this is what we've broken down our A union B. We've broken down our A union B into probability of A intersection B complement plus probability of A intersection B plus the probability of A complement intersection B. So we all know that A intersection B complement can be broken down as this minus this minus this. That is small b minus everything in A. And what is your small b? Your small b is what? A intersection B. So we can definitely break this down as probability of A, that is the whole thing here, minus small b, which is A intersection B, minus probability of A intersection B, minus probability of A intersection B. This, everything here belongs to this only. You will still do for this and this. So probability of A intersection B remains probability of A intersection B. Probability of A intersection B remains. So we want to break this down as well. So we want to remove, if you need this only, we have to remove this from this. And remove this from the entire list. And the entire list is probability of B plus probability of B minus small b, which is A intersection B. A intersection B. A intersection B. So you can now simplify this. You can simplify this. So if you simplify this, you can see that this cancels out this. So what are we doing? We are left with probability of A plus probability of B minus probability of A intersection B. These are the two. So look at the first theorem. The theorem of compare it with this, so you can see that it has been proved. So it is very easy. It is very easy. Just know your idea of your Venn diagram and be able to think very fast. So once you can think very fast, then you'll be able to. And as well, make sure you practice. So for you to understand it better, for you to remember, sometimes it is not that you don't know it, you know it, but you might have forgotten. So for you not to forget, so make sure you practice over and over again. So we have another theorem which is related to the last theorem. Theorem 5. So theorem 5 is basically the advance of theorem 4. That is they are similar actually, because theorem 4 is dealing with 2 events, but theorem 5 is dealing with 3 events, that is A, B and C. So if just the same statement that if A, B and C are three events in a sample space, so we can now say the probability of A union B union C should be what? The probability of A plus probability of B plus probability of C minus probability of A minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C minus probability of B intersection C plus probability of A intersection B intersection C. So as you see, it is very similar to the one of 2 events, but there is a little bit of modification here. For that of 2 events, you have probability of what you have here plus probability of what you have here minus probability of the intersection of the two. Similarly to this, probability of what you have here plus what you have here, that is probability of this plus probability of B plus probability of C minus the probability of each intersections, A intersection B, A intersection C, B intersection C. But once you subtract those 3, then you have to add the intersection of the 3 together. You have to add the intersection of the 3 together. So now let's go where it is that. So that's it. Include. So since we know that the probability, so we have the probability, this is what we want to prove. A union B union C. A union B union C. And you can apply our distributive law to this. If you apply the distributive law to this, then we have the probability of A. So recall that the probability of A intersection B union C. Recall that the probability of intersection B union C from the distributive law is basically the probability of A intersection B union A union union A intersection C. So from distributive law, this expression can be written as this. So you just include the probability sign. So A intersection into bracket B union C can be written as intersection B union intersection C. From the distributive law. And already proved from the first theorem. Already proved from the first theorem that this anything union can be written. And you know, this is already two events. You regard everything here as one event and regard everything here as one event. So you want to rewrite, and we have union in between them. If you want to rewrite it as as a theorem 4, then it becomes what? Probability of A intersection B, right, plus probability of A intersection C minus probability of A intersection B intersection A intersection C. From your theorem 4, just regard everything here as one, like theorem 4, which is A B. So you regard everything as if they are a single entity. So that's why we came up with all this. So we can recall that the probability of A union B union C can be written. You can write this as the probability of A union B union C. That is, we treat this as one entity. So let's call this one equation 1. So we can treat this as one entity and apply theorem 4. So if we apply theorem 4 to this, what will we have? We have probability of A plus probability of B union C, right, minus probability of A minus probability of A minus probability of A intersection B union C. A intersection B union C. And you can see from your equation 1, you already have A intersection B union C. So you can see this is equation 2. Let's call this equation 2. So substituting this equation into this, what do we have? So we have probability of A union B union C will be equal to the probability of A plus the probability of B union C minus equation 1. We don't want to substitute everything here into this. So what do we have? We have probability of A intersection B plus probability of A intersection C. Mind you should give this a bracket because it's going to affect everything you want to introduce. Plus, and now we have minus minus probability over A intersection B intersection A intersection C. So we derive this from distributive law. This is from distributive law. This is derived from distributive law. Why this is just a normal usual manipulation, you know. Just keep this one in bracket and you apply your force to it. So opening this bracket, we have probability of A plus probability of B union C minus probability of A intersection B minus probability of A intersection C plus this becomes plus probability plus that minus there before plus probability of A intersection B intersection A intersection C intersection A intersection C. So what do we have finally? We have probability of A plus we can as well break this down. Union here is not decided, so you can break it down into probability using your fourth theorem. So you can say probability of B plus probability of C minus probability of B intersection C using the fourth theorem, right? Minus probability of A intersection B minus probability of A intersection C plus, and you know, A intersection B intersection A intersection C will definitely be A intersection B intersection C, because you are now having A intersection A twice. So for intersection A intersection B intersection C intersection A intersection C can be reduced to probability of A intersection B intersection C. So we can now write this finally as probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of A intersection B intersection C, which is finally 2, which is equal to probability of A union B union C. So you have to know those theorems off hand. You have to know those theorems off hand. So in the next lesson, we will be discussing about some soft examples on probability in general, and we'll be moving to conditional probability and some other aspects of probability. If you're new to this channel, make sure you like, subscribe and share the video to those who find it helpful. Thank you.